An IMU stands for Initial Measurement Unit. It's one of the most basic sensors for robotics, but also one of the most difficult ones to deal with. Now we're going to dive deep into how an IMU works, and we're going to look specifically at the 9 degrees of freedom ICM-20948. The MPU6050 is a popular 6 degrees of freedom IMU, but it is quite unreliable and sensitive to noise. Instead, we will introduce the 9 degrees of freedom ICM-20948. It is a more modern and it is less prone to drift. We will code with ESP32 in VS Code and display the data in MATLAB. The hardware is quite simple. We will use an ESP32 as usual. Again, a breadboard and DuPont cable are not recommended as it can be quite unreliable. It is even more critical as the I2C communication of the IMU is very sensitive to noise. A custom PCB is used in our example. The tracers keeps the system compact and pretty. PCB without SMD components are cheap and quick to manufacture. And if you don't have access to a PCB manufacturer, I would suggest to use a 3D printer case for an ESP32 and the IMU with DuPont cable connecting the pins directly. Note the orientation of the IMU. The x-axis is pointing forward, the y-axis is pointing to the left, and the z-axis is pointing upward. In terms of connection, we're going to use only 4 pins of the ICM-20948. The VCC is connected to the 3.3 volt of the ESP32, the ground are tied together, and then the SCL, which stands for clock, and the SDA, which stands for data, are going to be connected to the pin 21 and 22 of the ESP32. To get the data from the IMU, we will code our ESP32 with VS Code and platform IO. In the file platform.io.ini, make sure to include the library from SparkFun and set the monitor speed to 115,200. The IMU is equipped with a DMP, which stands for Digital Motion Processor. We will use it in order to obtain the quaternion, gyroscope, and linear acceleration data. Make sure to uncomment the line 34 in the ICM-20948 header file located deep inside the SparkFun library. Let's take a little bit of time to explain the code related to the IMU. First, let's have a look on the main file. First, we are including all the library that we're going to use for the project. Then the void setup with the Arduino framework is where we run the code once in order to initialize the serial communication and the IMU. Then the void loop is where the code is repeated indefinitely. First we get the IMU data, and then we're going to print this IMU data on the serial communication. Reading the serial communication here is not going to be used. The IMU begin function is quite straightforward. First, we're going to initialize the I2C communication. Then we're going to initialize the use of the DMP. And then finally, we're going to calibrate the IMU. The IMU calibration function is used to have a proper initial data when we turn on the IMU. We will average the first 100 data. Note that the gravitation acceleration is subtracted in the z-axis. Now let's explain the function IMU getData. First, we're going to obtain the quaternions. We're going to obtain it through the DMP. In order to get the proper value of the quaternion, we need to normalize it. After getting the quaternion, we're going to get also the two other set of data, which is the gyroscope, and then again, we're going to obtain it through the DMP. Please note that we are subtracting the value of the calibration in order to get the real value of our gyroscope. And we do exactly the same thing for the acceleration. Finally, a note on the serial data print. We would like to display the data that we have obtained on the serial communication. It's going to be quite useful in order to display the data on MATLAB. Please note that the data is first starting with the opening arrow. Then we're going to display the quaternion, the gyroscope, and the linear acceleration. And then we're going to close our data with an ending arrow. This is going to be used in order to tell MATLAB the beginning of our set of data and then the end of our set of data. Before looking at MATLAB, let's have a quick look on the serial communication data. The first four numbers are the quaternions. Then we have the gyroscope or the angular speed. Since the item is not moving, this is why we have 0 for all three numbers. Then finally, we have the linear acceleration. Note that the z-axis is pointing up, but the gravitational acceleration is positive. Now we have rotated the IMU by 90 degrees. The x-axis is pointing up. Have a look on the linear acceleration. You can notice that now the gravitational acceleration is in the x-axis. Here our IMU, we didn't move it, so this is why the gyroscope is at 0, 0, 0. Now let's have a look on the quaternion. It is unnatural for us to talk about quaternions. Something that we are understanding a little bit more is the Euler angle. By using some quaternion to Euler angle translation, we can see that we have an angle of 10 degrees, an angle of minus 95 degrees, and an angle of 12 degrees in the X, Y, and Z axis. Does it make sense? Well, here you can see that we have rotated around the x-axis. Did we rotate in a positive direction or in the negative direction? Here you can see that we have rotated in the clockwise direction, which is negative. Finally, let's have a look at this case scenario. This time we have now rotated by 90 degrees around the x-axis. Note that the y-axis is pointing down. Regarding the linear acceleration, we can notice that the gravitational acceleration is equal to minus 9.8, which makes sense. The angular speed is still 0. The system is not moving. Then regarding the quaternion, let's use a translation from quaternion to Euler angle. And here we can see that in the x-axis, we have rotated by minus 87 degrees. Does it make sense? Well, we have rotated around the x-axis, but did we rotate it in the positive or negative direction? Here we can see that we have rotated in the negative direction. So everything makes sense. It's always important to verify that our data makes sense before jumping into MATLAB. Now let's try our sensor with a little bit more dynamics. We have verified that the statics value was quite correct. But what's happening if we try to move our sensor a little bit more rapidly? One of the most important things is to notice that even after moving with quite a lot of oscillation, the sensor doesn't show any drift. And this is like a huge benefit compared to the MPU6050, which is very sensitive to noise, very sensitive to drift. Here with this sensor, it just works, which is perfect in order to have a reliable system. In conclusion, we have looked at our hardware, an ESP32 and an ICM-20948. We have looked at our software, which is VS Code, Platform IO, and MATLAB. We have tried the static and dynamic performance of the IMU. In the future works, we'll try to put everything all together. We will investigate a ballistic system with a DC motors and an IMU. Thank you very much.